Hello, my name is Bethany Nguyen, and today I will be demonstrating an introduction to triangle similarity. To begin, it is important to first understand the basic concept of what similarity actually is. Now, geometric similarity is essentially when two or more figures are the same shape, just not necessarily the same size. In this specific case, we are talking about similarity in triangles, which will be the shape we are using in this video. Here is an example to illustrate what I mean by similarity. Here is a regular triangle. I'll go ahead and label this triangle X, Y, and Z. And let's say that its side lengths are 30, 20, and 10. And these are its interior angles. Now, here is another triangle that I will label A, B, and C. And say its side lengths are 15, 10, and 5. And here are its interior angles. Clearly, just by looking at these two triangles, we know that they are not congruent, or exactly identical in shape and size. However, if we take a look at the side lengths of both figures, we can see that there is a pattern with the length of each respective side on the triangles. Additionally, each of the corresponding angles, which can be identified by these marks, are the same for both triangles. These characteristics are included in triangle similarity. But if we take a closer look at the side lengths of these triangles, we can see that the side XY is 30, which is twice the length of the side AB, which is 15. So to get from the length of side AB to XY, we multiply by 2. Now let's see if the rest of the sides share that same relationship. Seeing that BC has a length of 5, to get to the length of YZ, we also have to multiply by 2 to get 10. And finally, since CA has a length of 10, to get to the length of XZ, we multiply by 2 to get 20. Therefore, we can conclude that these two triangles are similar because they have a common scale factor of 2. Triangle XYZ is similar to triangle ABC, but the two figures are the same shape with congruent corresponding angles. The only difference is that one triangle is either scaled up or scaled down. More on the subject of common scale factors for similar triangles, we could take the information we learned and figure out a couple more things about the side lengths of some other triangles. I'll just draw some basic triangles for the sake of this explanation. We'll say that they're similar. Now, just looking at these triangles and knowing they're similar, we can say that side AB is equal to some scale factor, which we'll use the variable S for. Multiplying S by the side of XY, we would get AB. If this is the case, we can also figure out what side BC is, equal to that same scale factor, S. Multiplied by the side length, YZ. And finally, that must mean that the side ZX, which is right here, is equal to some scale factor BC. Then to find what the scale factor is, we just solve these equations using order of operations. Since the only expression we see on either side of the equation is multiplication, we could use opposite operations and solve using division. To start off, for this first equation, we would solve for s, and we would do this by isolating the variable. We would divide this part of the equation by xy, sorry if that's hard to see, and we know that what you do to one side of the equation, you do to the other. So we would also divide AB by xy. And then we would get S equals AB over xy. Then, since all the other equations are written similarly, we would do the same thing for each one to solve for s. S equals BC divided by YZ. And then S would also equal CA, this is supposed to be CA. CA divided by ZX. Now we can see that all of the ratios are equal to S. We can go ahead and say that all of the ratios are equal to each other. So AB over XY is equal to BC over YZ, which is equal to CA over ZX, which is all equal to our scale factor S. From this, we know that with similar triangles, all of the ratios of corresponding sides are equal to each other and the scale factor. Now, I briefly mentioned congruency earlier, and that just means that two or more figures are exactly the same shape and size. You could translate them, rotate them, or even reflect them, but they are still identical shapes that you could make lie completely on top of each other and not overlap. Congruent shapes are also similar by nature because if a shape is congruent or identical to another, of course they would have to be the same shape, which is what similarity is. To sum up a lengthy definition, on the other hand, with shapes that are similar, they are the same shape, but with these you could translate them, rotate them, flip them, but you could also dilate them. And what dilating is just basically what we talked about with the triangle side lengths. It's essentially figures scaling up or down in order to make them identical. In this explanation, we aren't doing any transformations, so we won't need to dilate shapes or anything, but if you did want to make similar shapes congruent, that is what you would do. Now, let's go back to our triangle example. Since we know that triangle XYZ is similar to triangle ABC, that also means that their corresponding angles are congruent. That would mean that angle ACB, which is right here, is congruent to the corresponding angle XZY, which is right here. And the same would be for the rest of the angles. Angle CAB would be congruent to angle ZYX, and angle ABC would be congruent to angle XYZ. Now, let's say you're given a problem and it tells you that two triangles are congruent and they tell you two of the three corresponding angles. If the problem is asking you to figure out the last pair of corresponding angles, all you would need to do is figure out the third angle of one triangle, since similar shapes have congruent corresponding angles. This would be fairly simple to do using the triangle angle sum theory, which states that the sum of interior angles for all triangles is 180 degrees. And there you have it. Again, my name is Bethany Nguyen, and this is my demonstration of an introduction to triangle similarity.